This is the first
喂喂，我直接数1、2、3、4、5、6、7、8，1、2、3、4，1、2、3、4，1、2、3，没有连上去。
This is the first time that we built a headset and experience that combines higher than retinal resolution experience together with very high brightness as well as high contrast and high fidelity rendering scenes. So this headset has
喂喂，麦克风测试。喂喂，麦克风测试，麦克风测试。应该没那么快，要等一下下。
有听到吗？那你要不要再听？
喂喂喂，有听到声音是不是？好，那就没问题。好，OK OK，好好好，拜拜。
还是有的。
有，没问题。
谢谢谢谢谢谢。好，测完了。好，拜拜。
Good morning, everyone. Welcome back to 3DSA and IP 2025 Joint Conference. So we will start from our today's joint plenary session this morning. And let me welcome the Technical Program Chair, Professor Lin Huangyan, to host for the session. Welcome.
Good morning, everyone. For 3DSA people here, or for IP people upstairs. It is our honor to have Dr. Geng from Meta for the plenary speech. Let me introduce Dr. Geng first. She holds a PhD in optics from University of Rochester. Dr. Geng is a research manager of optics, photonics, and light system at Reality Lab Research, Meta. Where she did investigation in advanced optics and display technology. Together with her team, Melissa had explored the pancake optics, carrying them from the early incubation to successful transfer to products. More recently, she had led the efforts to create hyper-reality reality VR demo. Melissa's prior research also include study on high-resolution retinal imaging using adaptive optics. The title of her talk today is Pushing the Limits of VR Displays without breaking them. So let's have a big applause.
Thank you so much for the intro, Professor Lin. It's a great honor for me to be here today. I have an uncle who was a physics professor in Taiwan for many years, and he really enjoyed it. And I've always wanted to come to visit, so I really appreciate this opportunity to be here. I'm super happy to be here. So my name is Melissa, and I've been doing research in optics for about 20 years. The first 10 years, as you've heard, I've spent most of my time in University of Rochester in the US working on retinal imaging, medical imaging. And then I spent 3 years in Corning, New York, doing telecom and display optics research. And then starting in 2015, 10 years ago, I started my 10-year journey on AR and VR. So today I will share with you my stories of how I kind of lived the double life as a researcher over the past 10 years. So we worked with multiple technologies that you can see. So on the left, you can see that we worked on Fresnel optics, pancake optics, and other things. And we got them mature enough to tech transfer to the product side and eventually get into consumers' hands. And that is what I call our day job. And at the same time, we have this side job, which you could say that's even more important for us as a researcher, which is we push the limits for what the technology can do, can eventually become, and then we develop experiences that show us a glimpse of what the future can hold to drive research directions. So we have enjoyed developing new experiences, for example, building VR headsets reaching like 2 times the retinal resolution, like 120 pixels per degree, for example, or 200 degrees of field of view where you could basically see behind yourself in VR. And we also invented new ways to push the limits for AR and VR displays and trying not to break them. So that's our side job as a researcher. So here, I will also share with you a side story on AR, some fun inventions that we made, where the learnings that we had from VR actually helped cross-pollinate the AR research side. And then at the end of the presentation, I hope you will appreciate all of the customer-oriented breakthroughs our teams had made that led to better experiences. But even more, you will also appreciate the power of research for us to push the limits on what the future might behold. And then to end the talk, I'm going to share with you what's next, what excites me personally, and what do I want to do for the next 10 years for my career. So how do I begin? Let me start from this, how I got excited on this 10 years ago. So 10 years ago, I interviewed at Oculus Research. And what was eye-opening for me, which I'm sure a lot of you have also seen, was this Oculus Rift prototype that was soon to be launched. So that was my first VR experience. And as I was standing on top of that building, I know that there's no way I'm in danger of falling, but it seemed so real to me that I just couldn't move my legs, because the headset was good enough to trick my brain into believing that I'm somewhere else. And over the years, I had lots of fun demoing the Rift to other people. Like my mom, for example, there was this dinosaur scene in the headset, and she saw this dinosaur walking over her, and she had to kneel down like this and make sure that the dinosaur had walked past her and is not coming back. And my dad was also becoming an avid user of VR and had lots of fun with my Rift when he was visiting me. But if I look into the optics and display itself, it was super simple. It was just this pair of magnifier plus the phone screens. However, when you put this together with the rest of the system, magic happens. So at the end of my interview, I had a discussion with Michael Abrash, the chief scientist of Reality Labs Research. And he shared something like, we all have many choices in terms of what to work on, but it's always going to be exciting if you choose to work on something that we think will eventually land in the hands of over 1 billion people and invent the future. So what do we think the future is? We believe that the next revolutionary computing platform will be VR headsets as well as these stylish AR glasses. And that's been the belief for the past 10 years. So what if you can just put on a headset or a pair of glasses and you can be transported to thousands of miles away to attend a conference like today's, a class, a sports event, or a birthday party, and you can feel like you're just really there in person. So we believe that one day this will enable billions of people to meet, play, work, and learn with anyone, anywhere in the world. So let's take a look at how I experienced it over the years through the progression of the Meta VR headsets. It all started from DK2, which was a dev kit with a healthy amount of duct tape. And Meta acquired Oculus VR in 2014. And after that, Scott McEldowney founded the optics research team, and I joined in 2015. So the next year, Oculus Rift shipped and kicked off the modern VR era. The Rift was great, except that it had this what people call God rays issue, which is basically a stray light from the Fresnel lenses. So our team invented a solution that significantly cut down on the stray light. This invention, you can see, it dramatically improved visual clarity in Fresnel lenses, and it got shipped in Quest and Quest 2 headsets. And then Quest 2 had become the most popular VR headset of all time. And I did an internet search, and it says that Quest 2 had shipped 20 million units. And then another complaint on VR that I got is that it looks like you're just putting a lunchbox on your face. So in 2016, we started exploring pancake optics, and then research took a while, and then getting research to the product also took a while. For pancake optics, it took 6 years, from 2016, when our research started, to product shipping this in Quest Pro and then Quest 3. And today it's become an industry standard for VR. So later I'll share more about the key challenges we tackled to improve our form factor and content for contrast for pancake optics. And again, that's our day job for the tech transfer part. And at the same time, as we live this double life as researchers to push on the limits for what the research path could be by building VR headsets reaching very large resolution, very large field of view, and other key metrics, we figure out how to make the virtual world to be indistinguishable from the real world. So that's our other mission. And this, sometimes when we try to push on the limits, it breaks the form factor because maybe it becomes too large and too not practical. But it's fine for research because we're we would like to see what the experience would look like, and we call these time machines because it gives you a glimpse of what the future might hold. And after you see that, we then figure out, oh, this is the important thing, and we focus on this, and we figure out how to get back to normal form factor and practicalities. And then other times we invent these new solutions that push the limits without breaking them. And of course, our vision for the next revolutionary computing platform, as we heard, includes both VR and AR. So for the first 5 years in Meta, I worked pretty much exclusively on VR displays and eye tracking. And then the past, starting from like 6 years ago, my team and I also started working on AR research. So this recent years, Meta has shipped Ray-Ban Stories and Ray-Ban Metas. It shows the potential for future AI glasses, even though it doesn't quite have a display yet. And last year, we also introduced Orion, which we believe is the most advanced AR display, AR glasses that's ever been made. There's been many years of display research from our bigger team that went into it, and we're very proud of this. Today, I'll also share a side story on our AR research. So now I'm going to go deeper on each one of the stories from our 10 years of double life on both the tech transfer focus path as well as the research focus path. And let's start from Fresnel optics. So here are all of the current viewing optics families for today's VR displays. DK2 was the simplest thing, this magnifier. It's a simple refractive clear lens. And then Rift, the demo that I tried during my interview, used a pretty simple Fresnel lens. But at least it reduced the form factor by a lot. And then later we explored something like this pancake optics, which is a polarization-based on-axis fold optics. So Rift was great, but when one of my colleagues showed it to his wife, I don't know how, you can see all of the tails, right, even in this room. His wife was like, honey, can you turn off the light? When she was seeing the demo. And she was just in the headset, there was no light on. So we realized that we have a problem. We have a straight light problem. So normally, when people make Fresnel lenses, people would just make the unusable draft facets, because you have to basically collapse the magnifier lens down to this Fresnel, and you have this extra draft facet, and people just usually make them to be as steep as possible so that you minimize the footprint of the draft facet, and that's how people usually make it. However, this draft facet, even though you don't want it, it can still reflect light the wrong way, and that it will reflect light to the wrong directions, and that gives you the stray light. And we looked into various different ways to mitigate this stray light, and we ended up on a pretty simple solution called dynamic draft, which was, we basically just aligned the draft facets with the chief rays to minimize the reflections. And it turns out the fix not only helps with stray light, because this is not as steep of a drafting as normal, it also made it much simpler to mold and fabricate. So this solution was really was very quickly adopted and shipped, which drastically improved the contrast in our products. As you can see the result on the right-hand side. So left-hand side was previously what was shipped in Rift, and the right-hand side was what was after the improvements, what you get. So if any one of you have a Go or Quest 2, which again the internet says it shipped 20 million units, you have a piece of our research work. Now, is there a research threat to Fresnel lens too? There is. So it turns out dynamic draft kills the majority of the stray light, but there's still some remaining tails. And we did some further research, and we invented a new method to completely eliminate all of the stray light from the Fresnel lenses. This is actually a video on this side, but there's, at least from simulations, there's no stray light at all. So what we found is that for some of the field locations, we can find the perfect drafting angle such that there is just no stray light possible for the whole eye box. And then for some other few locations, this was not really possible. So we devised a new strategy, which is we just make the draft facet to be more shallow. So instead of, before we went a little bit more shallow, and now it's even more shallow. And the straight light, you still have straight light, but we directed the straight light to be out of the eye box. Now this solution works really well in theory, especially if you have the facets are very sharp. But the only problem is that now, because the draft facets are wider and darker, because they're shallower, we start to see the Fresnel rings. And this is an exaggerated version of what you might see. And we now need dynamic uniformity correction. So we talked about research on straight light and image quality. What about the rest of the metrics? And here are a few of the metrics that we normally track. So usually for research, we start from the product baseline. And then we believe that we need to eventually expand all of the performance axes to the max to be able to push the limits for visual quality. And now I'm going to walk through each one of the axes one by one. So let's start from resolution. Today we all have like retinal displays, right, on your phone or on your monitors, and people just don't like seeing pixels. When we do see pixels, there's usually two reasons. The first reason is usually just that there's just not enough pixels. When you try to spread this around such a huge field of view, there's not enough pixels. And the second reason is that sometimes the pixel field ratio is too small and you're seeing them. And the second one is actually much easier to solve. For example, if you have an OLED display, there's a lot of dark black matrix in between the pixels, and this is easier to solve because you just need to somehow fill in all of the dark gaps. So many years ago, I made an engineered diffuser, or you can just call it a grating, to fill in the gaps. And you just put this on top of the display, and it does work. So you can see that with the engineered diffuser, the image resolution maintains, but the screen door is significantly reduced. However, we thought about this more. There's something actually better than the screen door film that tackles both the screen door phenomenon as well as brightness efficiency. In other words, you can both improve the brightness and mitigate the screen door. So if we put a lancet array on top of the display, and again, it needs to be very close to the pixels, so normal cover glass wouldn't work, you can end up filling in the gaps to mitigate screen door while increasing the apparent display brightness. It sounds a bit counterintuitive from like an undue perspective, but for low field ratio displays like the Rift, you could actually get like more than 5 times of brightness enhancement, which is a lot. And then, of course, we spent a lot of time trying to enhance field of view. The human field of view is huge compared to today's headsets. We tried 2 different approaches here. We tried both tiling, which uses multiple displays and optics per eye, and there's like different tiling approaches. And we also tried this non-tiling approach, which involves using multiple elements, like multiple Fresnel lenses in this case, and then we do some canting or tilting, and we also played with distortion to give you wider field of view and reduce the drop in resolution. At the end of the day, and again, this is many years ago, we got to like 160-degree field of view using Fresnel optics and same size as the Rift. So what would be my ideal Fresnel lens display? This is not something that we've actually built, but I think if somebody is able to put all the building blocks together, we could get to a very wide field of view headset using Fresnel lenses, and then if you get to high dynamic range display with the OLED, and it wouldn't be too bad, right? But we will still struggle with the form factor and resolution, because even the diffraction limited resolution from Fresnel lenses is going to be limited by the pitch of your Fresnel lenses. Now, how do we address this lunchbox form factor issue? And that's when we started researching on pancake optics. So pancake optics stem from the pancake window in pilot training coves, like from the 1980s, long time ago. It is basically an on-axis polarization folding solution to drastically reduce your form factor. Now, basically, light comes from your display, goes through a bunch of polarization components. It hits this reflective polarizer and gets back reflected. And then in the reflection path, it hits the quarter wave plate twice. And by the time it reaches your reflective polarizer again, the polarization rotates and light goes through into your eye. So Pancake has the potential of transforming this lunchbox form factor into something that eventually looks like sunglasses. And of course, there's always no free lunch. So the Pancake optics is just like infinity mirrors, right? You have numerous potential straight light paths that can generate ghost. And the second thing is that the on-axis fold requires hitting this 50% beam splitter twice. So if you hit 50% twice, you end up with 25% brightness drop, 25% brightness at max, theoretically. And lastly, it's tough to get all of the polarization components to work across the visible spectrum and across all of the field of view. And stress birefringence of the lens can also show up in colorful patterns, as you can see, if you don't manage it well. So we developed numerous technologies to improve the Pancake contrast over the years, and we studied things like surface interactions and polarization management, the annealing process of the plastic, and anti-narcissus fumes, for example, because you don't want to see yourself in the lens. So these are all mirrors, right? And at the end of the day, the Pancake contrast did improve. And you can see that from something like the low contrast on the left side many years ago to the higher contrast on the right. Now, research to product on Pancake was a very challenging task. On top of all of the scientific challenges that we tackled, like pupil swim and ghost and contrast, like brightness, non-uniformity, and power, there is also a ton of engineering challenges that our product team friends tackled, like lamination process, assembly, thermal, and shape for the molding lenses and low birefringence. So as I said earlier, it took us 6 years in total, including over a year when we worked as a single integrated team together with our product friends to ensure a successful tech transfer. And at the end of the day, Pancake shipped in Quest Pro and Quest 3, reducing the optical module's thickness by 40% while providing even sharper visuals. And getting Pancake optics tech transferred is something that I'm personally very proud to be a part of. So what research did we do on Pancake to push on the limits? In the early days when we had much lower resolution displays, we tried all sorts of ways to improve on resolution. For example, we tried tiled displays, and we also tried high resolution inserts. So many years ago, I tried tiling 4 micro OLED displays using fiber optic faceplates, these tilted ones. It was really difficult to even just make sure I turn all of the displays on between the 8 displays for 2 eyes. And we also tried, so for inserts, high resolution inserts, for example, we tried tiling a smaller field of view waveguide display on top of the main Pancake display. And we learned how challenging it is to even just to maintain the color non-uniformity along the seams over temperature and over time. We also, another thing we tried is that we invented a switchable Pancake high-resolution inset. So what we did is that we came up with this Pancake lens that has 2 different focal lengths that can be switched using a switchable halfway plate. So if you have one focal length that gives you a lower resolution but large field of view, and then if you switch to a different focal length, it gives you a higher resolution but smaller field of view. And if you're able to have a high frame rate display and you just keep switching within your frame rate, this could be a high resolution inset display, but it uses a single display, but you're just switching in the time domain. So we're still waiting for this high frame rate display to enable this. Now, and then on field of view research, 9 years ago, we designed these 210-degree field of view Pancake optics, and we actually made them like 9 years ago. At the time, we were limited by the available film lamination process at the time, as well as the low resolution display. So resolution and form factor were pretty bad for this. However, this very large field of view headset was an unforgettable experience if you have a chance to try it. This is the type of time machine that once you try it, it was really hard to go back to the normal field of view after seeing this. Now, to get back to smaller form factor, we explored different things, including these tiled light field displays, where we added light field or MLA optics, micro lenslet array optics, to normal pancake optics. So in the center of the field of view, normal field of view, you still use your normal pancake optics, and then for the peripheral, like all the way to 200 something degrees, we actually use the curved OLED display together with these lenslet array. So these are custom light field optics that we used and built. And then on visual comfort and accommodation, I think a lot of my colleagues have talked about these over the years. There was a lot of different prototypes built by both our team as well as our sister team, Display Systems Research, using either switchable liquid crystals or just mechanical shifting of individual components like either the lenses or the displays to tackle the divergence accommodation conflict. And then on high brightness efficiency, I'll just give you a high-level example. Like we worked on laser backlighting for LCDs, and there's many different ways to do that. But for normal LCDs, you start from LEDs, and those photons just go wherever they want, right? And after going through all of the LCD backlight films, you lose a lot of light. Now, because if you are able to use lasers, we can aim to generate them at the right locations with the correct wavelengths and polarizations and in its own designated directions. So with that, you could potentially remove the polarizer and the color filter if you go to like a pixelated or patterned laser backlight, and you could potentially gain a lot higher brightness and efficiency using lasers. And laser backlight is also a key enabler for something like this hollow cake, also from our sister team, Display Systems Research, that uses liquid crystal-based diffractive optics as the thinnest pancake you could get. So these diffractive optics are so dispersive that they need very narrow bandwidth lasers to maintain the resolution for not on-axis but off-axis. And that's basically it for the pancake research trajectory that we've been building, and all the way down to the smallest form factor. Now I'm going to talk about the side story on AR. So how many of you have wrapped up research in one area, and one day you suddenly wake up and you realize, this might actually also have some important applications in somewhere else? So in our case, I suddenly realized that a lot of the work that we were doing in Fresnel lenses and pancake optics can actually be applied to AR as well. And I'll give you a couple examples. So for eye tracking, usually at least many years ago, we needed like a 45-degree hot mirror between the lens and the display to allow for on-axis imaging of the eye using infrared light. However, you can see that as we go to pancake optics, there's not enough distance between the lens and the display to fit this 45-degree mirror, and you'll end up seeing the edges if you just use a small one, edges of the mirror. So we had to come up with a new invention. So what we did is that basically we just collapse the hot mirror into Fresnel lenses or prism facets, and then we coat them with the hot mirror coating so that infrared light can be reflected and go to the eye tracking camera. And then we immerse these Fresnel lens facets such that the eye can see through this as a transparent sheet. So this eye tracking prototype actually worked pretty well. And the idea also inspired AR research, and the variation of this later became the eye tracking method for the Orion AR glasses. We didn't quite use Fresnel's, it was more like a diffractive or holographic approach, but the basic idea is the same. And then in this second example, it was pretty fun for me to do. 6 years ago, I had the task to design the smallest zonal illuminated FLCOS projector for AR. And as you know, for Orion, we are aiming for this 70-degree diagonal field of view. And it was kind of like an impossible task to get to like a 70-degree field of view with and I was asked to do like a extremely small form factor, like less than 10 by 10 by 10 millimeter squared. So we need to image an array of mini LEDs onto the LCOS or the FLCOS. And most of the methods we thought about at the time was kind of large. Because it needs the critical illumination and also double telecentric lenses for these LCOS illumination systems. So we started thinking about how do you make something smaller? Now, pancake lenses had enabled us to get to the smallest form factor VR, and I started thinking about could it help us here as well? So I tried an on-axis fold, just like a pancake here. And then I added in another lens to make it double telecentric. But again, like pancakes, it still only has 25% efficiency. However, for VR pancakes, we had an invention to have like a symmetric path to double the efficiency, so that like for a pancake, you can overlap a signal path with the ghost path. I didn't draw it out here, but like you can see there's a lens that's completely symmetric to this. And if you overlap it really well for pancake, it can give you double the efficiency. But for imaging, it's super difficult because if you want to overlap them completely, it's extremely difficult. But for illumination, you could actually do it. And then as I thought about it more, and that's when I had this punch a hole in the moment, punch a hole in a type of a moment, I was like, why don't I just try to break it? So I decided to remove this 50% mirror in the pancake, and then I punched a hole. I punched the hole in the pancake cavity, so that I just have like 20% central obscuration. So this became a pseudo pancake with a hole in the middle and a high 80%-ish efficiency. And this ended up getting a huge numerical aperture and a good magnification between the mini LEDs to the LCOS panel. And it was also double telecentric. And best of all, this whole thing was tiny in design. It was only 7 by 7 by 7 millimeters squared. It was not much larger than the beam splitter itself with the 70-degree diagonal field of view. So it was a lot of fun to work on this. Even though it didn't quite go to Orion, I had a lot of fun, and I think it's one of those punch a hole type of moments that will light up the future, maybe for somebody else. So now going on to the last section. So you've seen and learned how we navigated Fresnel lenses and pancake optics, both in terms of tech transfer and the research path. And I hope that you enjoy this little side story on AR, where we punched the hole into this pancake to produce a little projector and LCOS illumination. Now what's next? What gets me excited for the next 10 years? So there are two key themes that follow the trajectory of both our tech transfer path and the research path that I'm personally very excited to continue to push on to become the next revolutionary computing platform. So I'm investing my team in both paths, and one is focused on minimizing size and weight, closer to like the tech transfer path. And this will eventually I want us to eventually get to the comfort of glasses. And I believe that when we get to the comfort of glasses, that will be the day that we move beyond phones. And the other path is focused on maximizing the visual quality. And when you put the headset and glasses on, it's going to transport you to a whole new world where you are going to be immersed in a 3D hyper-real world, and it's going to be hard to distinguish what is the real world and what is the virtual world. So that's the visual quality path. It's going to enable brainstorming and debating and whiteboarding with our remote colleagues as easy as it is with colleagues sitting next to us. And when that happens, I believe we will move beyond both laptops and TVs and Zoom meetings, of course. So how do we move beyond phones? We start from minimizing the size and weight. We previously talked about our solutions for very small form factors, such as pancake and hollow cake, and those are getting closer and closer to glasses form factor, except that both of these prototypes are still tethered, and they don't have some of the sensing capabilities. And then talking about glasses with sensing capabilities, let's go back to AR and AI glasses. So the Ray-Ban Metas are growing in popularity since it was released in 2013. We worked with EssilorLuxottica, our partner, and they recently shared that the sales for Ray-Ban Metas the sales revenue has more than tripled year over year. So more and more people are starting to like them. So the Ray-Ban Metas has RGB cameras, it has audio interactivity, and hands-free connection to AI. And now we're watching the world to adapt this new wave of AI glasses. And I imagine that when we combine a lightweight display with these AI glasses, the marriage of wearables and contextual AI will transform personal computing. It will eventually become more invisible, interfacing for us across language boundaries and anticipating the information we need in the moment. So I look forward to my future travels when, if like I visit Japan, my glasses will translate everything for me in real time and guide me through the subway system to where I would like to visit. It's gonna create my own personal itinerary according to my needs, and it will be my own travel guide 24/7. And also I don't even need to carry my phone for any of these. It'll remind me where I left my wallet, my keys, and when I need to send my kids to soccer, and so forth. So to sum it up, when you meet me in a few years in the future, hopefully you will find an upgrade, like a much smarter and more organized version of myself. However, we're talking about an auto wearable device that allows us to move beyond phones. And size and weight is a huge remaining challenge, especially when you want to combine AI glasses with a display. So if you look at Ray-Ban Metas, they're 48 grams. And the Orion AR glasses with this immersive field of view were 98 grams. And even small field of view information glasses with binocular, if you look at their display weight, the weight is usually like 30 grams. On the other hand, I weighed my own glasses, and my own glasses are less than 30 grams, and I'm even a very, very high myope with -8 diopters. So we have a big challenge here. So somebody will have to think through, does our current display architecture really hold up to these weight requirements? What can be done to minimize the weight for the display stack, the sensing suite, the frames, and the batteries? And what can we do to make them look like real and fashionable glasses that we will all want to wear? So to go to an all-day wearable device, we need to do things that we didn't think was possible. So size, weight, and power of AI glasses, I believe, is the next frontier to enable moving beyond phones. And then what about the other paths? How do we move beyond laptop and TV? So I'm going to share our latest progress here. Now, for many years, we have been on a mission to do what we call passing the visual Turing test, where we attempt to create virtual experiences that are indistinguishable from the physical world. And last month, my sister team, Display Systems Research, and my team did public demos at SIGGRAPH in Vancouver, where we showed demos, and these demos reached new milestones toward this mission. So my team's demo was called Tiramisu. It was a hyper-realistic VR experience. So we built this time machine that gets to 3 times resolution and 14 times more brightness than Quest 3. And then when you combine this with high-fidelity rendering scenes, this became the most realistic VR scene that I've personally ever seen. It was really pleasant to look at. So we got a lot of positive feedback from people who saw the demo. For example, David Hinley from Upload VR describes it as a stunning window into another world. This is the first time that we built a headset and experience that combines higher than retinal resolution experience together with very high brightness as well as high contrast and high fidelity rendering scenes. So this headset has 90 ppd compared to the 26 ppd that you have from Quest 3. It also has up to 1400 nits of brightness, which is 14 times that of Quest 3. It also has high contrast optics and display built in.
Here is an overview of the nature scene. Here you can see all the different types of environments that we have, all the rocks, the trees, the vegetation. So here's a park sign. The 90 ppd allows easy legibility of text, even at small, minute details on this park sign. And then finally, we have a nighttime scene. This nighttime scene shows off the dark levels that the OLED display can achieve, as well as the very bright speculars that we can get as well.
So the video actually doesn't do it justice. This is the type of thing that it's kind of like if you see a 4K TV or an HDR TV for the first time, you really have to see this in person, and I hope that maybe someday I'll be able to show these demos to you. This is the first time that we built a headset So for the research path, we start from these time machines because tiramisu is like really large and heavy to give you a glimpse to the future. And then after we find the experiences to be good, we would prioritize the experience. And then the next step is to invent new components or architectures to get to the not breaking form factor type of actual prototype to maintain form factor and manufacturability. So for tiramisu, the current experience uses a huge headset and a very small field of view, like 33 degrees. And we do have a future paper design to go back to similar to Quest 3 form factor and field of view, while reaching a balance of high retinal resolution and high brightness and contrast. We haven't verified the design yet, but if it works, this could open up a whole new space outside of the Fresnel lenses and pancake optics and go to high dynamic range VR someday. And where tiramisu sacrifices on field of view, our second demo from Meta, Boba 3, from our sister team, Display Systems Research, fills in this gap. So 9 years ago, we showed like a similar headset, but it was huge. Now, over the 9 years, there's been new process development and much better displays, and that has enabled a much nicer form factor on this wider field of view pancake headset compared to what we did 9 years ago. So Boba 3 has a horizontal field of view 180 degrees, a vertical field of view of 120, and both are much larger than Quest 3 with a form factor and resolution comparable to today's consumer VR headsets. So here's a video that will give you a sample of this demo. On the left-hand side, you're going to see a VR headset, and the right-hand side is a headset that adds in mixed reality digital pass-through of the real world, also in wide field of view. And in the actual demo, you can toggle between the normal Quest 3 field of view and the 180-degree field of view. And again, this is one of these experiences that you just have to see this in person to feel the difference. Because again, the video wouldn't give it justice. So what are the remaining challenges to tackle before VR replaces laptop or TV? So I think there's 3 things. Firstly, we still need to combine all of the good things together, like this hyper-real experiences between high resolution and high brightness and contrast, wide field of view, and everything else. And secondly, all of these will need to be miniaturized into a small form factor. And lastly, on top of all of these, if we want to interact with our remote friends and families and colleagues, we need a way to bring people on the other side into the 3D virtual world. And how to do that realistically is another key area of research. So there you have it. You've seen how we live double lives as researchers. We tech transferred low straight light Fresnel lenses and pancake optics to eventually get into tens of millions of consumers. And at the same time, we worked on the research path to push on the limits of VR without breaking them. You also saw some of our latest research as we build out the future for what's next. And as I shared earlier, for the next 10 years, I'm excited about the next revolution for personal computing. And thank you for welcoming me to tell my story. I look forward to hearing from those interested in also in the future of AR and VR and collaborate on this exciting journey forward. Thank you so much.
Melissa's talk about pushing the limits to XR experience. Any questions?
Yeah, my question actually is about holography. Holography was really mentioned very often, but I think it's triangulation. So you have really two displays, and you can see in a three-dimensional way by triangulation. Is there also hope that a true holography will be coming to the metaverse? For example, for augmented reality or virtual reality, that you have not actually really for a three-dimensional image only one distance. That's actually the case if you have triangulation. You have one distance to the display. At holography, in a true way, the distance is variable.
Yeah, thanks for the question on holography. So I think we see holography as having a lot of different advantages, right? There is the distance, or there's solving the divergence accommodation conflict. There is also, for example, you can just solve the RX issue without adding additional elements, right? There's a lot of different things. It can create a real, even for a single eye, a real 3D world. I would say that in Meta, we are still working on holography. There's still a lot of interesting research that we're doing on both VR, AR, and XR side of the house. And we are also looking at other ways to solve accommodation, like, for example, the two things that I mentioned using some type of switchable LC elements, or even just moving the display. So if we just want to solve the distance or the accommodation issue, we don't know if holography is the best thing to do, at least for the near future, based on the practicality. But long term, we still think that holography is one of the most interesting areas to look into. I don't know if that answers your question.
Okay, because of time limitation, so you can make exchange during the breaking time. Thanks, Melissa again.
Thank you so much for having me.
Announcement. Next session will begin at 9:55. Hello, it's time. I'd like to open this next session. Welcome to this session. This session is about contact lens display. I'm Yasuhiro Takaki from Tokyo University of Agriculture and Technology, and he is also chair.
I'm co-chair of this session, Kenji Yamamoto from Tokushima University.
This session is about contact lens display, and I think the contact lens display is the ultimate form of AR display. And recently, several contact lens displays have been proposed. This session was proposed from Japanese committee, and we think this is the right time to conduct a special session for the contact lens display. And we have 2 invited speakers and 4 regular papers. So I'd like to introduce first invited speaker, Professor Hirotsugu Yamamoto from Utsunomiya University. I think all of you know him. He is the investor of air system, but he has another face. He is a leader of standardization group of ITU. So please welcome Professor IEC. So please welcome Professor Yamamoto.
感谢邀请我来演讲。Thank you very much for inviting me to give this talk. I'm Hirotsugu Yamamoto from Utsunomiya University, and this talk have 3 parts because, as introduced by Professor Takaki, I'm many years engaged for aerial display, and recently we have published the first international standard at IEC TC 110. This is the first part, and this approach is, I expect that this approach is applicable for the contact lens display. This is because, and the third part is the reason. In Japan, Ministry of the Trade and Economy is promoting the Japan Model Standard Acceleration Scheme. That is a dual approach, advancing R&D and also standardization in parallel. So I will show this approach. Firstly, what's the aerial display? You know that the aerial display generates images that appears to float in midair without the use of physical screen. They create illusion of real, tangible object popping up, allowing for touchless interaction, similar to what is often seen in sci-fi movies. So there's nothing but you can manipulate or operate the image in mid-air, and you can punch through it. The principle is very simple, just geometrical optics to converge the light in the mid-air. So there's nothing but when you place paper, then images formed on the prints. There are several optics using the reflection-based floating display and also reflection-based. The reflection base is one of the biomimetics optics, like lobster's eye, that has rectangular compound eye to converge light in mid-air. Recently, we are proposing the aerial display technique by use of retroreflectors. Retroreflectors, as you know, one of the most pervasive optical components that reflects the light, travel reversely to the incident direction. It is used for light-based traffic signs. And in combination with the half-mirror and retroreflector, that image is formed in the plane symmetrical position with respect to the half meter of the light source. So these features wide being angle and large size scalability and low cost and mass optics can provide this floating image. And recently we have realized the aerial hollow mask illusion, like so. And in combination with that touch sensor, then you can draw in the mid-air. There's nothing but there's a IR sensor is embedded and detects finger position. You can draw in the mid-air. And there's nothing, so in this case, this doors is augmented, one of the augmented reality display without needless to wear the AR glasses. These techniques have many. Recently, 4 companies from Japan produce these materials components. Pioneer and recently in the corporation now providing the dual layers micro lens array, and also Parity Innovation, which is a spin-out company from NICT, Japanese Research Institute, provides a dihedral corner reflector array, and also a company in Hiroshima called ASCANet produce aerial imaging plate or ASCA 3D that has closed slit mirrors arrays. And also our group propose aerial image by retroreflection, AIRR. And there are many pros and cons in bright image blur and viewing and so on. Recently, we introduced polarization modulation to increase light use efficiency, and so there are many types of the aerial imaging optics, and advantage and disadvantages here. So in this case, the set maker will confuse which is better, so. And there are some durabilities sometimes change, and also there are sometimes ghost image or stray light is become noticeable. So to compare these many components, it is important to some measure or performance index. So we started international standardization activities. Aerial display was selected as a preliminary working item. This is the first step of international standardization in 2018. And I am the project leader from the start of PWI on aerial display. The first stage is that before the international standardization track, because this technique was not published in that. Recently, it is published in Japan and also becoming popular in worldwide. But in this, before the COVID-19, this one, it is not popular. So the first step is to publish a technical report. Technical reports are entirely informative, not normative. Technical report focus on particular subject and contain, for example, data, measurement techniques, test approaches, case studies, and methodologies, and other type of information that is useful for standards developers and other audiences. They are never normative. And in this case, a TR is approved by simple majority of participating IEC member countries. The first technical report was published in 2020. In this technical report, we define the aerial display in strict meaning. But this is a background class. Before this definition, there are many types of display that is sometimes called aerial display. In this table, the image is formed real image in the term of geometrical optics and virtual image. A famous aerial display is so-called Pepper's ghost. There's no the image is not the collection of the focus converging rays, but the image is a collection of the focus point made by extensions of diverging light. This area. And also, sometimes transparent display is also called aerial display sometimes. So, but our focus is this area. There's no hardware or on or in front of the image. For example, holographic display and light field display also can form real image. There's no hardware on the image. And also some information screen that is formed use of passive optical components. When I started the project, there are several groups. Korean National Committee proposed proceeded holographic display standardization and also the light field display. So if we propose a project that may be covered by another project, it is not approved. So the first step is that to define that technology that is not covered by the ongoing project. That's an important point. So I define the like this area display in strict meaning, which requires international standards for industrial and commercial applications. In order to realize prospective applications of aerial display includes the direct handling of the image in the mid-air for the terminal and also aerial signage for the general public. In order to realize them to make basic usage, there are 5 requirements. Aerial image can be handled with the naked hand, and the image position is the same and stable for everyone. And the image is visible with the naked eye and display is as safe as the conventional display and mass productive and the conventional. So aerial display in the strict sense is defined here. That aerial display forms a real image in mid-air by use of an incoherent light source display and passive optical components to converge diverging light from the light source display. These limitations are necessary to avoid the overlapping with the holographic display project and the light field display project. This definition was approved, and this TR technical report was published. The next step is international standard. International standard is a document that has been developed through the consensus of experts from many countries and is approved and published by a globally recognized body. It comprises rules, guidelines, processes, characteristics that are used to achieve the same outcome time and time again. This definition given in all IEC standards is normative different. Normative. It must document developed according to consensus procedures which has been approved by IEC National Committee members of the responsible committees in accordance with Part 1 Directive. Because IEC is one of the bodies recognized by World Trade Organization and entrusted by it for monitoring the national and regional organization agreeing to use IEC international standards as the basis for national or regional standards as a part of WTO technical barriers to trade agreement. So this is important to promote the business. And to publish this IS, there are 7 stages. The first stage is preliminary working idea proposal. And the second stage and third stage, and so blah, blah, blah. So for the aerial display, there are many key performance indices, floating distance, image size, position, and also beam position, and light resolution, and so on. And this importance is different for the applications. Just touching application and also the AR, VR, or general use. In that case, its resolution is very important. So under this condition, firstly, we wanted to focus on this resolution. But the situation was changed because of the pandemic of COVID-19. ARL touchless interface is that prevents spread of infection. So ARL touchless switch becomes very important. So we focus on just 3-dimensional position and the luminance measurement of the standard. So because ARL display, ARL panel, operation panel needs exact matching of the image position and also sensing position. So in 2021, new work item proposal. This is one of the biggest hurdle to proceed to the international standardization. This requires approval of 66.7%, and also the participation of at least 5 countries is necessary. It is approved, and the final stage is also approved. Then, in 2024 January, the first IS was published. Then this is the main topic of this session. Now I'm engaged in the project on contact lens display. What's the reason why I'm a project leader of contact lens type is that funny story. But before this appointment, I was appointed to the head of delegation of Japan National Committee. And at the plenary meeting, I was just have the meeting of the Japanese secretary. So absent from this working group 12 that deal with EI display. And we are in the first floor and discussing another one. And at the third floor, this IVR display was discussed. And one of the project leader, the former project leader was an expert from Hitachi Corporation, but he was moved to another section. So then the project may be disbanded. So another one just to raise hand, and Professor Yamamoto will succeed his project while I was absent. But all the members agreed with that one. So I was appointed with this project. And also one of the member, expert from the Belgium, Dr. Dieter Kuipers, he's a researcher on contact lens display related technologies. He agreed to co-PL. And this content was discussion with, we maintain this draft with Dr. Kuipers. So firstly, smart contact lens is defined that contact lens that provides functions beyond the reflection correction. and this market market focus is very positive. In general, smart contact lens type can be broadly categorized based on whether they form an image on retina or not. This classification supports the classification of scope, functionality, and standardization direction for contact lens type displays, and so on. This is a rough classification of contact lens type displays based on image forming functionality. So smart contact lens is classified to two categories: non-image forming and just sensing or image forming. No image forming, but medical treatment used for assisting viewing external display. That is contact lens type display in broad meaning. And the image forming type and off-cornea display source, I think the second speaker in this session will report the development of cornea display source. And the external display source is placed near the cornea. Image forming optics are placed on the cornea. Is a middle meaning. And on cornea display source, the research holographic microwave and so on, several optics and the light source embedded contact lens. This will be the contact lens type display in strict meaning. Perhaps second speaker will show that many development, but this Google or SenseMed, this company already developed the smart contact lens for sensing, mainly glucose density and so on. And some smart contact lens type for medical treatment. And also the co-project leaders, Dr. Cooper, IMEC, developed this guest host LCD inside the contact lens. You can see this material, and by changing the applied voltage, this transmittance is changed. So variable aperture, and this the size is. Please notice that these are fingerprints. So this optics is embedded on the contact lens. And another approach is contact lens type with smart glasses. There are lenses within a lens and to view the micro display. And another in that research articles, micro-frenzy type or meta surface is proposed. And in Japan, Professor Takaki leads a new project with NICT, and they integrate the ultra-thin holographic optics and also ultra-small electronics and packaging, and developing the ultra-small and thin SLM. And also how to show the image is also investigated. And Professor Takaki's approach will be given the invited talk in IP this afternoon. And also I was built a prototype of holographic contact lens display. I think this figure, this photograph, and also the movie is gain the approval of the many experts in the IC meeting. That in this case, the static hologram is recorded in photopolymer and attached the contact lens. And when the camera is here, so you can see that image. So this prototype shows that the contact lens display is not a dream; it's near features technology. So, but there are many challenges. Contact lens type requires the following features. This A to C is lectures from Professor Takaki, visual comfort and wearability and perception. And also, the IC expert insists that ISO compliance non-display functions maintaining compliance with the ISO standards on contact lens. That there are 19, at least 19 standards related to contact lens. This should be applied for contact lens display. That will be the next hurdle. But for the tier stage, just showing this, okay, and we have proposed a Q document, is a question document. Do you agree to start the project or this technical report? Is okay. Then the result, voting result is approved. So now committee draft is being circulated. So it's circulated until next week. And we'll collect the comments and revise the contents. So in the current stage, these are table of contents, contact lens type, technology, and classification, as I said, introduced, and functional element approach to image formation, and also performance characteristic specification, luminance, contrast, resolution, and so on. So like this one. This is the current stage of the standardization activity on contact lens type. And finally, I'd like to introduce our Japanese initiative, dual approach, advancing R&D and standardization in parallel. In Japan, METI has launched this model. This initiative promotes collaboration among universities, industry, and government agencies to align innovation goals with international standards, particularly in fields such as display technology, imaging display technology. So until now, that with the market, price and quality is important. Consequently, high quality products were sold. And until now, fundamental standardization was limited to the fundamental activities. Standardization focused on quality assurance. But from now, recently, price, quality, and new value access is important. So growing need for market creating strategy is important. So in that, as for the standards, so this strategic activities, so standardization activities integrated with business strategies. So in my case, I'm engaged on the global outreach and collaboration. We are building international collaboration with partners in Europe, Brazil, and Asia. Demonstration and validation at large-scale events are key expansions. This is a French magician. He's using the area display for magic. These are activities in Malaysia, Hungary, Brazil, Copenhagen, Denmark, and Kenya. And also, we have installed the ER display in a museum in Brazil. Recently, this ER display was stolen. So someone wanted to use that. And first, recently, we have an exhibition at Osaka Expo. In June and August, we have at the robot and mobility station, and this collaboration work with robot laboratory. This robot attracts the user and showing the aerial image for aerial signage. And also this has aerial terminal, touchless terminal. By pressing this button and start chasing the user. Then let me conclude my talk. Aerial and contact lens type displays are advancing towards practical deployment, highlighting the needs for harmonized evaluation method and international standard. ongoing effort under ICTC 110 supported by national initiative and real-world demonstrations are building the foundation for safe, reliable, and social accepted adaptation of these emerging technologies. They also thanks Professor Takagi and the expert of ICTC 110 for their valuable input. 非常感谢你的聆听。
Thank you very much for very nice talk. I can accept only one question because the time is limited. Do you have any question? No? So thank you very much, Yamamoto Sensei. I'll introduce our second invited speaker, NtuEE. The title is Development of Holographic Reflective Contact Lens Display Using Curved Volume Holographic Optical Element. He will show us excited contact lens technique.
Yeah.
Start.
Hello everyone. My name is Jinsul Lee from ETRI of South Korea. And I'm gonna speak about the contact lens display with a hologram. So the title is Development of a Holographic Projection Contact Lens Display Using a Curved Volume Holographic Optical Elements. So before we enter the smart contact lens display, I have prepared some slides for the contact lens basics. So for that, actually the contact lens can be classified several types of contact lens. So if you are for example, if you are proposed to, you can classify contact lens as purpose and wearing location, material and the wearing period. This kind of the purpose can be classified contact lens, which contact lens who you use. So usually in the market, they classify the contact lens as a scalar and the semi-scalar and the corneal. So the scalar lenses looks like that. So it covers the entire eye. So it usually used for the movie. So if for the daily use, usually we are using semi-scalar and the corneal lens. So corneal lens means the hard lens in the market, and semi-scalar lens is a soft lens in the market. So, yeah. As you can see under the figure. Oh yeah. On the figure, the corneal lens has a small diameter, and the semi-scalar lens is much bigger than corneal lens. So it covers some portion of the scalar. So anyway, we can categorize it, the contact lens like this. So if you want to make the contact lens, you have to consider this optical configuration. So usually these days, the contact lens has a tri-curve structure. So this one is first curve, this one is the second curve, and this one is the third curve. So to keep comfortable wearability, usually tri-curve structure is often used to make a contact lens. So if you want to make some special display by using the contact lens, you have to consider the optic zone, this area. And the peripheral curve is actually does not affect to the vision correction. So usually the contact lens display company put the electric component, put the electric component on the peripheral curve. So yeah. In other words, if you want to make the contact lens or the contact lens display, you need to consider this kind of parameters for the for commercial market. So this is the basic of the contact lens display design. And this is another types of contact lens, which is called the hybrid contact lens. That means that rigid lens and the soft lens. That means hard lens and soft lens is integrated into the one lens. So the consideration is similar, but in the hybrid lens, you should consider the integration method like this type of process. So there is a big difference between the hard lens, hard soft lens, between hard soft lens and the hybrid lens. So contact lens. After you design the contact lens can be manufactured with this process. So in the case of the hard lens, usually using the laser cutting, there is cutting the lens surface with the blade. And if you want to make a soft lens, in the soft lens case, it's usually using the mold casting. That is the very cheapest way to manufacture the contact lens. So what is the contact lens? So usually the contact lens are using to enhance the visual to correct the vision. But usually in these days, the smart contact lens is a kind of the wearable device that integrated electric and optics such as biosignal and drug delivery and augmented reality display in addition to the vision correction. So I believe that the paradigm shift is going on from glasses to the contacts, maybe. I hope so. Yeah. So unfortunately, there is so many smart contact lens articles and paper patents are reported on the online, but unfortunately, there's the most of studies are focused on the diagnosis on the biosensing, like a biosensing, or the pressure, drug delivery, like that. So the AR display is conducted only at the very small groups. That is good news for us, but because that means that, in other words, that means we have a lot of issues to solve in the field. So anyway, in detail of the smart contact lens display, we can see these kind of papers in the online. This one and this one is the excellent research result of the Professor Takaki, and the other research is also related to the smart contact lens display, but actually there's no practical experiment by using the real contact lens. That is just a conceptual result for the contact lens display. So another report of the smart contact lens is that of company is that Mojo Vision and Expansio. Actually, the Mojo Vision is shifted their company from smart contact lens to the micro display company. So they did not research about contact lens anymore. So recently, the Expansio, there is a startup company, is funded by maybe Dubai. Anyway, they got a lot of money to developing the smart contact lens. So as you can see in this video, by using the contact lens, we can see the images. So they have a plan to integrating every from sensing to display into the contact lens, maybe in future. Yeah. So from this slide, this is my story. The motivation when I started this project, actually, most of everyone focuses on the glasses. I believe that the wearable devices, typically glasses and contact lenses, but why everyone focuses on the glasses? I think that maybe contact lens can be another solution for the AR or VR display technology. So I focused on the contact lens. And that time, the video, the drama of the Palace of Alhambra is the broadcast on TV in South Korea. there's kind of AR contact lenses, the drama. Yeah, this drama is so sensation to me. So I really impressed with this scene, and then I started to this project to see the hologram with contact lens. So firstly, I imagine that this kind of system, if somebody who wearing a contact lens, and the contact lens just deliver the information to the retina, the information is coming from the outside project, like that. This kind of project transfer the hologram to the eye, and the eyes of contact lens deliver the information to the retina. So this kind of system can be realized in the near future to see the hologram with the contact lens. So to do that, I have to make there's some kind of special optical component to make off-axis beam delivering. So I designed the curved volume hologram optical element, so like this specification. So I designed with the GMAX, and then we analyzed the diffraction efficiency of the volume hologram. So for that, I calculate the preformed surfaces, diffraction efficiency of the preformed surfaces. So because you know that usually Kogallic coupled wave theory is assuming that the volume holographic optical element is on the plane, not a curved surface, just a full plane. So in the curved surface, you have to calculate the local point diffraction efficiency to get an entire field diffraction efficiency distribution. So the first step is to find the normal vector of each local point. The normal vector can be calculated by this dot product, and after get the local vector, normal vector, and then we can calculate the diffraction efficiency of each local point. So by doing it iteratively for the entire field, we can get a 3D information of the diffraction efficiency of the entire field. So this one is the contact lens lesion. The red ring is the contact lens lesion, and this is the diffraction efficiency distribution. So this is a 3D plot. This is cross section of X and Y. So, but you know that we are just using we just need only small portion of the contact lens because we are using the volume hologram on the contact lens. So our volume hologram is cut by 5 millimeter to 2.5 millimeter. So we just need this small region of interest area. So finally, we can estimate the entire diffraction efficiency distribution in the volume hologram, curved volume hologram. Curved volume HOE. So to optimize the recording condition, I did the simulation for the diffraction angle, average diffraction efficiency variation depending on the recording angle. So as you can see in this figure, actually the 27 degree is the best condition for the highest diffraction efficiency, but in our practical experience, we are choosing that 30 degrees for the recording angle. So that is because the diffraction efficiency is not difference much more. So we set 30 degrees is the best condition for the recording. And then we also did we also analyzed the angular deviation of our recorded hologram, recorded curved volume HOE. So as you can see in this left figure, the TPX efficiency is decreased dramatically according to the angular deviation of the recording angle. And then we did also the simulation of the reconstructed hologram's quality. So as you can see, the first law means that the equation efficiency maps of the cupped volume SOE. So, and the reconstructed result of the hologram, as you can see in the left right column, show that very poor, because the TPX efficiency is directly affected to the hologram information. So So I also did another simulation for calculating the angular deviation, TPX efficiency variation depending on the wavelength deviation. So as you can see in the left slide, left figure, actually the wavelength deviation is not an important factor to ensure the TPX efficiency of the contact lens display. So we also did the simulation, and the simulation also shows that law was to the wavelength deviation, as you can see in this first law and first column and the last column. So there is no image quality degradation. So finally, we are optimized the curved volume holographic optical element condition like this. So we select the contact lens properties and the curved volume holographic optical properties, and the recording conditions choose. And then finally, we made the contact lens looks like that. This is the where's the point? Yeah. This is the entire contact lens. This contact lens is specially designed by us, which is the diameter is 10 millimeter, and the thickness is 100 micron. So to make such a contact lens optical component, we designed upper contact lens and the bottom contact lens. And then the volume hologram optical element is inserted inside the both of them, and then attached with the optical adhesive, and then recorded with this kind of optics. And so we did several types of contact lenses like that, like ice plate, like a circle, and the rectangular. Various types of the volume holographic optical element are inserted into the contact lens to make a perfect image quality of the hologram. So we also designed the holographic projector, but this is the very basic optical configuration of the hologram, because we are just want to know the feasibility of our proposed system to see the hologram with the contact lens. So we built this system, projector system looks like that. The contact lens attached to the iPhone here. And to cover the eyes and head movement, we also designed the tracking system to cover the small eye box. So we are designed the movement system, and then the movement system can cover the maybe 48 degrees field of view. So this is the last result. So this is the old one. Maybe we call that prototype 1. This is a prototype 2. So as a result, we still have a problem like a color dispersion from the outside light, like a sunlight. But yeah, I think that by using contact lens, the hologram or the other kinds of displays scenes can be see clearly through this result. Yep. So unfortunately, I did not capture the full color hologram because of the experiment issues in our lab. But I captured so I just captured the RGB, the images separately to see the feasibility of our system can show the hologram with the full color. Yeah, this is conclusion. We did the holographic projection contact lens display system by employing the curved volume hologram, curved volume HOE, and conducted the diffraction efficiency analysis on the preformed surfaces to validate optical feasibility. And finally, we built the contact lens and the hologram projection system, and we can see find the feasibility of the contact lens holographic contact lens display as future AR devices and XR devices. And before the end of this talk, I want to introduce our labs what are doing. So we are doing this kind of display. We are doing every kind of display optical systems in our lab. So the first one is the automotive holographic head-up display that is proposed to replace the head-up display in the car with the hologram. So this is very, very hard, difficult, and costful project because, but we are developed very small the optical engine for using in the car, which has 5 liter volume under. So in the near future, if I have another chance to share our research about the head-up display here, that would be a good use for us. And another thing is the light field display, which has adaptive function. Yeah. And the final one is per-pixel infinite depth 3D display. That is kind of the split Loman multifocal display, which is announced in the 2027 in Carnegie Mellon University in US. So we developed that technology. We advanced the split Loman multifocal display to another advanced system. So yeah, like this. This is a conceptual image, but anyway, we are trying to make it compact and make the compact and integrating the entire system with the eye tracking like that. So this is the result of our lab. So as you can see in the video, each OLED pixels can have the depth as a per pixel. So the depth can be changed without using any hologram, just using optical characteristics of the lens. So, yeah, thank you.
Thank you very much, Dr. Jin-Soo Lee. Is there any question from the floor? We have enough time.
Thank you very much. This is wonderful talk. I have one question. So, with this use case, so projector is required, right?
Yeah.
So then, contact lens itself is very small, but looks like the peripherals projector. Suppose we have large field of view, so we might need to have very large combiner. Am I correct? For projector has to shoot eye, as well as keep angle of incidence with respect to HOE.
Yeah. So we are in the holographic projector are using the Fourier optics, Fourier hologram types of the hologram. So in this project, yeah, this optics just make the holograms like the viewing window in the at the pupil position. So the holograms is in the converging at the viewing window. So if you put your eyes with a contact lens at the viewing window, you can see the entire field of view, which is reconstructed by the holograms information at the viewing window. So it's a kind of keyhole display like that.
I see. So
Yeah.
second question, may I? So then suppose we actually move our heads, right? Then do we see image actually shifts? Right. Would that be a problem?
Yeah, maybe that is a big problem. So I imagine that the final application to avoid such a problem. So I advertise my technology to the audience as like that. So if you put your contact lens and hold your position, you can see the hologram, like your desk or the driving. As a kind of situation, you cannot move your head very much, or you cannot move your bodies because your seat or we hold the driver's the wheels. So in that case, maybe such a problem will be avoided.
Thank you very much.
Thank you.
Is there any other question? Okay. Yes.
Let me ask a question about the situation in Korea. Are there any national projects or collaborative research group in Korea related to a contact lens display?
Not yet. Yeah, actually, we are trying to make a government-funded project about this type of contact lens display, but we're still doing the fund. Yeah.
Thank you. Thank you very much.
Any other question? Okay. I have several questions. Could you describe the field of view of your contact lens display?
Yeah. This system has field of view is 15 degree. Yeah.
And what factor determine the field of view?
Actually, the field of view is determined by the pixel pitch of the SLM. In our system, we are using SLM, which is demagnified by using the 4F optics. So lens 1 and lens 2 is demagnified the pixel pitches to the half. So in our system, theoretically can be achieved 15 degree of field of view. But I think that in the experiment, I believe that actually practically it has maybe 10 degree maybe. Yeah, in the experiment. But practically 15 degree.
Yeah, HOE size does not affect the field of view.
Yeah, HOE is not an important factor for the field of view. It is also the size of HOE is the important factor for the eye box. Yeah.
So what the HOE size affect on, for example, resolution? The HOE size affect what does HOE size affect on?
The HOE size is depending on the radius of curvature of the contact lens. You know that if you put your paper on the cover surface, it is impossible, because so imagine that it is impossible. So put the paper on the cover surface. The paper should have very small width, very long dimension, small width and long length. So for that, maybe in our experiment, we are using the radius of curvature is 8.5 millimeter. In such a system, in such a configuration, the 5 millimeter by 2.5 millimeter is the best to attach the HOE on the cover surface. Yeah. So maybe it is determined by your contact lens shape.
Okay, thank you very much. My final question is, how do you provide a curved shape to your hologram?
Excuse me.
How do you provide the curved shape? How did you curve the hologram?
Yeah. That is so important question that actually we are pre-calculate the hologram according to the deviation of the deviation of the contact lens radius, because in this system the optical path length from here to here is a little bit different. So the hologram is like a tilted image is maybe displayed on the retina. So to solve such a problem, we compensate the hologram with a preset the phase lamp.
Thank you very much. So thank you again.
Let's move to the next paper. The next 4 papers are regular papers. The first regular paper is from Citizen Fine Device Corporation. The authors are Tomohiro Ando, Manabu Nakamura, Yuta Kanamori, Takuya Yanagisawa, and Katsuya Moromizu. If you can start, please start.
Thank you for the introduction. My name is Manabu Nakamura from Citizen Fine Device. Today I will be presenting on evaluation of the switching angle of ferroelectric liquid crystal and its influence on the characteristics of phase modulation holograms. At first, let me explain about Citizen Fine Device. We are a group company of Citizen Watch. We manufacture automotive parts, quartz crystal units, and small LCD panels. Since 2000, we have been producing ELCOS microdisplay products using ferroelectric liquid crystals. ELCOS stands for liquid crystal on silicon and refers to a type of reflective LCD panel. In addition to FLC products, we also undertake the prototype manufacturing of pneumatic liquid crystal panels and optical devices. Since last year, we are involved in collaborative research aimed at realizing holographic contact lens displays. Our role is to conduct basic research towards the development of ultra-small and ultra-thin spatial light modulators. I would like to give you a brief explanation of the holographic contact lens display. An ultra-compact SLM is built into the contact lens. The SLM displays a hologram pattern and generates a wavefront from the illumination light. The wavefront is projected onto the retina, and any image can be superimposed on the field of vision. This image is a mock-up of the SLM currently under development. It is still very thick, so we will continue to work on thinning it. What type of SLM is suitable for holographic contact lens display? An SLM using pneumatic crystals is ideal due to its excellent multi-tone capabilities. The main material we are developing is pneumatic. However, SLM must be ultra-small, ultra-thin, and ultra-low power consumption. There are so many constraints, and considering these problems, I think FLC are also viable option. I would like to talk about light modulation using FLC. The left figure shows the behavior of an FLC in SS-FLC mode. Yes, this figure shows. FLC exhibit in plane motion similar to IPS LCD, where the switching angle between the two states is 2 theta. In amplitude modulation, efficiency is maximized when 2 theta equal 45 degrees. So many FLC developed in the past were designed with a switching angle is 45 degrees. On the other hand, for phase modulation applications, efficiency is thought to be maximized at a switching angle at 90 degrees. In reality, these are few FLC materials that can be used with switching angle greater than 45 degrees. As a result, we have not yet made much progress in evaluating what happens to hologram images at switching angle greater than 45 degrees. Therefore, in this research, we fabricated an FLCOS SLM with a wide range of switching angles and evaluated the effect of the switching angle on the efficiency of the phase modulated hologram. This is a FLCOS SLM used in this research. It was previously developed by our company as a general purpose SLM. It has the advantage of high speed response and low crosstalk even with fine pixels. The pixel count is 1280 squared. The default switching angle is narrow 37 degrees, and since it uses FLC, the grayscale is limited to two levels. When this FLCOS SLM is actually operated using amplitude modulation and phase modulation, the display results as follows. Since it is a binary tone, a 1-bit bitmap image is sent. When amplitude modulation is combined with a polarizing plate, the standard display results as shown in the image above. When a binary CGH pattern is displayed using phase modulation, the characters C, F, D are displayed as shown in the image below. An experimental sample was created by injection of FLC with a wide switching angle into this FLCOS SLM. Two types of FLC materials were used in this experiment. Both were manufactured in-house. The central axis of the switching angle was set to align with the vertical pixel boundary line as shown in this image. In this prototype sample, the target wavelength at which half lambda is exhibited was set to a range of approximately 450 nanometers. By adjusting the drive voltage, we are able to obtain samples with 5 different switching angle situations from 41 degrees to 63 degrees. First, we measured the diffraction efficiency of the FLCOS SLM. The figure shows the experimental system used to measure diffraction efficiency. RGB lasers such as 450 nanometers, 532 nanometers, and 633 nanometer were used as light sources. The FLCOS SLM displays a binary diffraction grating image shown in the figure. The intensities of the zero order and plus minus first order light were measured, and the diffraction efficiency was calculated from their ratio. This figure shows a relationship between switching angle and diffraction efficiency. It can be seen that for all RGB light sources, the diffraction efficiency improves as the switching angle increases. The diffraction efficiency at 450 nanometers and 532 nanometer is significantly higher than that 633 nanometer, which is thought to be due to the retardation being set around 450 nanometers. Here, 100% diffraction efficiency indicated that the intensity of the zero order and first order light are equal. Next, the effect on the phase modulated hologram image was evaluated. This image shows a hologram display experimental system, which uses an LED light source with a wavelength at 470 nanometers. The LED light is collimated through a polarizer and lens, and then irradiated onto the FL cos SLM. The FL cos SLM is tilted 45 degrees relative to the incident light, and then so that reflected light is emitted upward. The SLM displays a CGH pattern, and the reconstructed hologram image is shooting with the camera. We created multiple states with different FLC switching angles, and each time shooted the hologram display image with the camera. The shooting conditions and light source intensity were fixed. It can be seen that the characters displayed by the hologram become brighter as the switching angle becomes wider. In conclusion, we have fabricated an FL cos SLM with a wide switching angle and confirmed that increasing the switching angle leads to improved efficiency of phase modulation holograms. Future challenges include numerical analysis of the brightness of the hologram image was not possible. Practical application of FLC with wide switching angles. Integrating SLM into contact lens displays. Many other issues remain, and we plan to continue our research in this area. This concludes my presentation. Thank you for your attention.
Thank you very much for your interesting talk. Okay, so are there any questions or comments from floor? Okay. Okay, so let me ask a question. Please go to the page 8, please. I would like to know how to see the diffraction efficiency. So in the case of 100%, does it mean no zero order beam, no second order beam, just one order beam? Is it right?
100% of diffraction efficiency is intensity of zero order light and one first order light is equal.
Equal. So in that case, 50% zero order beam and 50% one order beam. Is it right?
Yes.
Oh, okay, thank you very much. Okay, so are there any questions? Yes, please. Just a moment.
So I have a question about the final result. So I want to know the reason why なんだっけな、higher angle devices higher improved brightness. Reason why.
Reason why. At the phase modulation is FLC's switching angle is wider to output to light polarization axis is to same of two states, but phase shift of two states is just so bigger.
Thank you very much. So it's time to go to next presentation. So let's thanks to speaker again.
Thank you.
So the next presentation is from Yuto, Hayashi, Fuma, Hirata, and Yasuhiro Takaki from Tokyo University of Agriculture and Technology. Okay, so please start.
Thank you for introduction. I'm Yuto Hayashi from Tokyo University of Agriculture and Technology. The title of my presentation is Ultra-Thin Laser Backlight with under 0.1 mm thickness for holographic contact lens display. In order to realize the metaverse, further evolution of augmented reality technology is necessary. Recently, head-mount displays and smart glasses have been developed as AR devices. However, they are often heavy and uncomfortable if used for a long time. And so that's why contact lens displays are getting attention. They are small, light, and easy to wear. It could be the final form of non-invasive AR devices. However, there was a problem. The display in the contact lens is too close to the eye, so we can't focus on the image. To solve this problem, we have a solution. We have proposed a solution. It is holographic contact lens display. I'd like to introduce it. This display device doesn't show the image itself, but show a hologram pattern. By this method, the reconstructed image appears to be located away from the eye, so we can naturally focus on the image. Moreover, see-through display becomes possible using a phase modulation hologram. Holographic contact lens display is the only method that can achieve both thinness and high resolution. These systems consist of a transparent phase modulated spatial light modulator SLM, and laser backlight, polarizer, and laser diode. The light from laser diode is expanded by this HRE backlight. The expanded light illuminates this phase-only SLM, and this SLM modulates only vertically polarized light, and this laser backlight emits only vertically polarized light, and this polarizer transmits only the horizontal polarization component of the light from outer scenery. So this SLM doesn't affect the light from outer scenery and only modulates the light from laser backlight. And all of these components must be integrated into a contact lens. So ultra-thin structure is needed. So my research is fabrication of laser backlight to meet this requirement. In our previous study, we developed a laser backlight based on double-sided HRE structure as shown. However, achieving further thickness reduction remained a challenge. And so we proposed a laser backlight with a single-sided HRE structure and a thickness of less than 0.1 millimeter. Next, I will explain the principle of the laser backlight. In this study, the proposed laser backlight was designed referring to the waveguide used in Microsoft HoloLens. And this is our proposed laser backlight. HOE 1, 2, and 3 are positioned as shown. I will now explain step by step from HOE 1. First, the incident light is coupled into the waveguide by HOE 1 and propagate to HOE 2 based on TIR, total internal reflection, like this. And next, when the beam propagates to HOE 2, a part of the light continues to propagate in original direction, like this, while others are deflected by HOE 2 and propagate to HOE 3, as shown. So HOE 2 can expand the beam one-dimensionally. The same thing happens with HOE 3, so HOE 3 can expand the beam two-dimensionally. And finally, the beams are emitted from the waveguide and illuminate the SLM. To display the image with uniform brightness, it is necessary to illuminate the SLM with uniform illumination. To achieve this, we gradually change the deflection efficiency of the HOE. The deflection efficiency is initially lowered, like this, to deflect a part of propagating light. And by increasing the deflection efficiency, the light intensity directed toward HOE 3 can be made uniform. And the deflection efficiencies were determined using this equation. Next, I will explain the exposure of HOEs. Each HOE is fabricated using two defined beams. For HOE 1, beams A and B are used. For HOE 2, beams C and D. And for HOE 3, beams A and B. However, it is difficult to realize these beams with a single exposure system. So instead of beams C and D, we use the beams C' and D' traveling in opposite directions. This is because the interference fringes produced by C' and D' is the same as produced by C and D. Therefore, proposed laser backlight can be fabricated by these beams A, B, C', D', and E. Next, I will explain the exposure system. To fabricate HOEs continuously, we control the exposure partitions using two-axis automated stage and regulated the exposure time by shutter. And these animations show the system during fabrication of HOEs. And this is the exposure system. And this can produce 5 beams, as I mentioned. This is A, B, C', D', and E. And in our experiments, we use a photopolymer to make HOEs. And the photopolymer is Bayford HX200 from Covestro. And this photopolymer has 3 layers: cover film, photopolymer, and substrate. We remove cover film, and after that, we liquid HOEs in the photopolymer. So the photopolymer becomes HOE, and substrate functions as waveguide. So photopolymer and substrate are the components of laser backlight. Photopolymer is thickness of 60 micrometers, and substrate is 60 micrometers. So the laser backlight is 76 micrometers thick. So we have achieved an ultra-thin design of less than 0.1 millimeter thickness. And this is the thinnest practical configuration when using this computer, photopolymer. Next, I will present the fabrication result. And this is laser backlight we fabricated in this study. And this is contact lens. As you can see, it has been fabricated extremely thin. And this shows the laser being coupled into HOE, and the expanded beams are emitted from HO3. We observed that incident beam was expanded 4 by 4 times. The size of laser backlight was 4 mm by 5.8 mm. Next, I evaluated the emitted light. I measured the light intensity at 16 different points, calculated their average values, and assessed the deviation. The deviation was 23.1%. The cause of this deviation may include uniformity evaluations by visual inspections and light loss in the photopolymer. Next, we consider the tolerance for the refractive index of external material. When the thickness is 76 micrometers, the incident angle of the light propagating in the waveguide is 73.1 degrees. And the refractive index of the waveguide is 1.48. In this situation, to achieve total internal reflection, external refractive index must be less than 1.415. And silicon hydrogel is widely used for contact lens material. And the material has a water content water content ratio of 24 to 36%, and when used for contact lens material. Within this range, the highest refractive index is 1.40 at 24% water content. And this is less than 1.415. So the laser backlight fabricated in this study can operate sufficiently within the silicon hydrogel contact lens. In this study, we tested the laser backlight in water which has a water content which has a refractive index of 1.33. As shown here, expanded light is emitted from HO3. So this demonstrates that our technique can operate sufficiently underwater. This is summary. An ultra-thin laser backlight continuing the holographic contact lens display was fabricated with a thickness of 76 micrometers by using a single-sided HO structure. And the evaluation of the emitted light showed an overall light intensity variation of 23.1%, a deviation of 23.1%. We experimentally confirmed that the fabrication laser backlight functions in water instead of silicon hydrogel. Thank you for listening.
Thank you very much for the impressive approach that uses the substrate as waveguide. Thank you very much. Are there any questions or comments from floor? Okay, so let me ask a question. The current deviation is 23.1%. Are there any idea to improve the deviation?
Thank you for your question. We evaluated uniformity by visual inspection to make uniformity intensity uniform by visual inspections, and so to solve this problem, I want to evaluate emitted light from laser backlight with an image sensor and adjust the exposure time to achieve uniformity.
Okay, thank you very much. Okay, so time is limited. Let's thank the speaker again.
Thank you.
Let's move to the next presentation. The next is from Professor Mizushina and Kenji Yamamoto from Shinshu University. If you can start, please start.
Okay, thank you for introduction. My name is Haruki Mizushina from Shinshu University, Japan. I will talk about evaluation of apparent image movement caused by display delay in contact lens display. It's a human factor study in contact lens display, especially in human visual perception. So this is an outline of my presentation. First, I introduce contact lens displays and accompanying perceptual effects. Contact lens displays have been proposed as a next generation AR device. Contact lens is fixed to the cornea like this. So the displayed image apparently moves around the field of view with each eye movement as shown in this figure, like this. Therefore, to maintain consistency between eye movements and the view of external world, image updating according to the rotation angle of the eye is necessary. In this study, we call this operation rotation angle compensation. As shown in the upper figure, without rotation angle compensation, image is always in the direction of gaze. So image appears to move with eye movements. As shown in the lower figure, with rotation angle compensation, image is shifted in the opposite direction by the amount of rotation of eye movements. So image is perceived to be stationary in its original position in the external world. Rotation angle compensation is expected to function without problems if there is no display delay. However, rotation angle compensation requires time for detection of eye rotation angle and calculating and displaying of the shifted image. So the effect of display delay on image perception during rotation angle compensation needs to be clarified. So this study aims to clarify the effect of display delay in rotation angle compensation on image perception. An experiment system using an eye tracker is constructed to simulate the view caused by wearing contact lens display. And we simulate various display delay situations and identify the amount of acceptable delay. Then I move to explanation of experiment methods. At first, I explain principle of this evaluation experiment. The effect of time delay on rotation angle compensation in contact lens displays was evaluated using the following three conditions for image updating with rotation angle compensation. The first, image position on the display does not change regardless of angle of eye rotation. This simulates a compensation without delay, like this. Second condition, B, image position of the display moves with eye rotation. This simulates a situation of no compensation. The image sticks to the gaze position. And third condition, C, image position of the display initially moves with eye rotation and then returns to the initial position after time delay. This simulates situation of compensation with delay. This figure shows a schematic of the experimental apparatus. To simulate view of contact lens display, we used an eye tracker, high-speed eye tracker with 2000 Hz sampling rate to detect gaze direction of participants' left eye. Stimulus position and image update timing were controlled based on the direction of gaze detected by the eye tracker. The visual stimulus was displayed on a 23.8-inch LCD monitor located at the visual distance of 57 centimeters. The refresh rate of the LCD was 240 Hertz. It's a kind of gaming monitor. Participant's head was fixed by a forehead and a chin rest. The experiment was conducted in a dark room. On each trial, the participant first gazed at the white alphabet A, presented 5 degrees to the left of the center of the display. After a random interval of 3 to 5 seconds, a red circular target appeared 10 degrees to the right, and the participant moved his or her gaze towards it by saccadic eye movement, like this. In condition A, simulation of compensation without delay, the character A remained in the original position on the display. In condition B, simulation of no compensation, character A always moved in the same direction as the gaze position, like this. And in condition C, simulation of compensation with delay, the character A first moved in the same direction as the gaze, and after delay returned to its initial position on the display. At the end of each trial, the participant responded to whether or not character A was perceived as moving. Delay times for condition C were 10, 30, 50, 75, 100, 150, 200, 400, and 1000 milliseconds. Background was dark or natural landscape. 5 trials for each condition were tested. 3 females and 4 males with normal or corrected to normal vision participated in the experiment. Then I move to the experimental results and discussion. In the condition A, simulating compensation without delay, no image movement was perceived. In the condition B, simulating no compensation, image movement was always perceived. In the condition C, simulating compensation with delay, the results plotted on a graph. This graph shows the percentage of apparent movement of the image as a function of the time delay of the rotation angle compensation for one participant. The horizontal axis represents the delay time of the compensation, and the vertical axis represents the percentage of movement perception of the image. A delay of 0 milliseconds corresponds to the condition A, simulating compensation without delay. The results for B, no compensation, and with a delay of 1,000 milliseconds are not shown in the graph, but image movement was always perceived in these long delay conditions and no compensation conditions. Open circles and open triangles indicate results for dark background and natural landscape background, respectively. As shown in the graph, no image movement was perceived at all when the delay was less than 30 milliseconds. But the proportion of perceived movement increased as the delay increased, and the image movement was perceived almost every time when the delay was about 100 milliseconds or more. There was a tendency for movement to be more visible on the dark background than on the natural landscape background. The results show that the delay in rotation angle compensation must be at least about 100 milliseconds or less for rotation angle compensation without image movement perception. Okay. The results for the remaining 6 participants are summarized in this slide. Although there are some individual differences, everyone shows similar tendencies. Let's summarize the results so far. In this study, we built an experiment system using a high sampling rate eye tracker to simulate how images appear when wearing contact lens display, and simulated various delay situations for evaluating image movement perception. Results show that delay approximately 100 milliseconds or less is required for rotation angle compensation without image movement perception. All 7 participants in this experiment showed similar tendencies. Let's discuss these results. The results of this study are consistent with previous studies on visual perception. Bridgman reported in 1975 that sensitivity to image displacement decreases for several tens of milliseconds after saccade onset. Shioiri and Cabana reported in 1989 that sensitivity to image motion decreases for several tens of milliseconds after saccade onset. In this way, findings in vision science also support our results. Decrease in sensitivity to motion and displacement perception around saccade would determine the tolerance range for time delay in rotation angle compensation. Finally, I conclude my presentation. This study investigated the relationship between the delay of rotation angle compensation for image update and the perception of image movement in contact lens display. The results show that the images are always perceived as motion when the delay is longer than about 100 milliseconds. These results indicate that short delay is required for step or image perception in contact lens display with rotation angle compensation. These research results were obtained from the commissioned research by NICT Japan. Thanks for listening.
Thank you very much for your interesting talk. Are there questions or comments? Yes, please.
Thank you for your talk. Would you go back to the slide where you show individual differences, 6 people? Maybe the next one, I think. Yeah. So it seems some people like the middle on the top and the right, and the left hand side on the bottom, the subject is quite sensitive to the delay. So what makes the difference between those individuals?
Yeah. One possibility is that one is sensitivity for the image movement and motion, and another possibility is the difference of the decision criteria of the motion perception among the participants.
Thank you.
Okay, so let's thank the speaker again. Okay, so let's move to the final presentation in this session. This presentation is from Hanano, Takada, and Yasuhiro Takaki, and the presenter is Professor Takaki. So please start.
Thank you for the introduction. I'm sorry, the first author, Hanano Tanaka, cannot attend this conference. Instead of her, I will present this research. I'm the second author, Yasuhiro Takaki, from Tokyo University of Agriculture and Technology. The title is Neuron Pixel Camera for Contact Lens Displays. Contact lens display is an ultimate AR device that is non-invasive to the human body. Recent advances have introduced various ultra-thin imaging systems embedded in contact lens display. The pixel-by-pixel technique was proposed by University of Washington. They embedded the LED into the contact lens. Ghent University developed the curved shape LC liquid crystal element. Georgia Institute of Technology used meta surface lens. Microprojector technique was proposed by Mojo Vision. They developed a micro LED display. We proposed the holographic technique. Holograms generate images apart from the eye. The external projector technique was proposed by Dr. Lee of Italy, the second invited speaker of this session. In this study, we developed a new camera technique used in the contact lens. Incorporating a camera into contact lens displays facilitates gesture input and gait tracking functionalities. However, there are severe requirements for the camera technique used in contact lens: ultra-low energy consumption and thin form factor. This study proposes a novel contact lens camera using neuron pixels to minimize energy consumption and thickness. This slide shows the previously proposed contact lens cameras. Only a few contact lens cameras have been reported. The Mojo Vision reported a very small and low energy consumption CMOS image sensor at the IEEE conference. Sony's patent is well known. However, its patent is not about a new camera technique, but it's about system management, including a camera. This slide shows the neuron pixel camera proposed in this study. Two-dimensional array of neuron pixel, two-dimensional arrays of neuron pixels connected to a neural network. The neuron pixel consists of a microlens, 2D mask pattern, and photodiode. The microlens project the outer scene onto the 2D mask pattern. The projected image was multiplied by the 2D mask, and the photodiode output the sum of the product, sum of the multiplied image. So this sum of product operation is analogous to the biological neural unit. So the neuron pixels are optoelectronic implementation of neural unit. The output from the neuron pixels are processed by the neural network to perform various image processing functions. Because the length of the neuron pixel is approximately equal to the focal length of the microlenses, thin form factor is possible. I think some of you consider that the neuron pixel are very similar to the single pixel imaging optical system. That's right, the neuron pixel is based on the single pixel imaging, SPI. This slide explains the SPI. High-speed SLM is used to generate a series of 2D patterns which modulate the image, and the photodiode output the sum of the modulated image to provide SPI signal. In the reconstruction process, the SPI signal and 2D patterns are multiplied and summed to predict image. So the neuron pixels can perform SPI in a spatially multiplexed manner. Thus, the neuron pixel does not require a high-speed SLM. For the SPI, the use of Fourier or Wash-Adamar basis requires the number of required 2D patterns to reduce the number of required 2D patterns to approximately 5 to 10% of the target image resolution. It means that the number of neuron pixels can also be reduced. This slide considers the energy consumption. In camera, most electricity is consumed for switching to read out signals from pixels. Because of a large number of pixels, the CMOS image sensor consumes the highest energy. Because a high-speed SLM is not required for the neuron pixel camera, its energy consumption is the lowest. The throughput of the neural networks is usually higher compared to the conventional complicated image processing systems. Different types of neural networks can be connected to the neuron pixels. Classification network can perform gesture recognition. Regression network can track gaze. Generative network can reconstruct images. In addition to the weighting parameters in the neural networks, the 2D mask pattern in the neuron pixels can be learned to enhance specific image processing functions. When the transmission type SLMs are used instead of the static 2D patterns, the neuron pixel camera can support various imaging processing functions. Moreover, the photodiode array and SLMs can be implemented on one chip. This one chip implementation will create a new semiconductor. The preliminary experiment was conducted to verify the effectiveness of the neuron pixel camera. Instead of fabricating physical neuron pixel, a 2D image sensor and microlens array were used to simulate multiple imaging systems. The sum of product operation of neuron pixels were simulated using PC. This slide shows the experimental result for the image reconstruction. Fourier and Wash-Adams basis were used. The number of neuron pixels was changed from 10 by 10 to 22 by 22. As you can see, for the input images are rock, paper, and scissors. For the gesture recognition, 20 by 20 neuron pixels were sufficient. This slide shows the video of the image reconstruction. We used Fourier basis and 17 by 17 neuron pixels. Then the neuron pixels were connected to neural networks. We performed the gesture recognition. The number of gestures was increased to 9, as shown in like this. The resolution was 64 by 64. The number of training data was 630. The number of test data was 270. Two kinds of neural networks were used, DNN and SPI plus CNN. This slide shows the image classification using DNN. The number of neuron pixels was 149. The Fourier basis was used as the 2D patterns of the neuron pixels. It means that the 2D patterns were not learned by the neural network. The DNN consists of 3 layers. The batch size was 8, number of epochs was 500, loss function was cross entropy, and optimizer was SGD. This slide shows the prediction result for the test data using DNN. The prediction accuracy was 73%. Black shows the correct prediction and red shows the incorrect prediction. The accuracy using the DNN was not high. This slide shows the image classification using SPI plus CNN. First, the image was reconstructed using SPI. The resolution of the reconstructed image was 64 by 64. Then VGG19 was used as the CNN. This slide shows the prediction using SPI plus CNN. The accuracy was improved to 92.2%. In the experimental results shown in this study, the 2D patterns of the neural networks, neuron pixels were not learned. I think when the 2D pattern will be learned by using neural network, the accuracy will be improved. This is the conclusion of my talk. In this study, neuron pixel camera is proposed featuring ultra-thin construction and low energy consumption for integration into contact lens displays. Preliminary experimental validates image reconstruction capabilities using simulated neuron pixels. Beyond the contact lens displays, the neuron pixel camera can be extended to various applications in which ultra-low power consumption is critical. Thank you very much.
Thank you very much. Are there any questions or comments? No? Okay. Let me ask a question. So, in your study, in your experiment, the resolution is 64 by 64.
Yes.
How did you decide this number?
Yeah, our purpose is detect the gesture determination. So we try change the resolution from 16 by 16 to 256 by 2, and we think 24 by 24 is sufficient for gesture recognition.
Okay, thank you very much. Okay, so it's time. So let's thank the speaker again.
Thank you very much.
This is the end of this session, and the next session is poster session from 1 p.m. Okay, so
for 3DSA board member, we will have a meeting in the 7th floor. So the meeting room is 7A.
Okay, for the board meeting, please visit the venue directly without taking over the lunch boxes. It's all prepared. Yeah, thank you.